Educational Module. Machine Learning. Learning Unit. Core. Semi-supervised learning. Semi-supervised learning is a class of machine learning tasks and techniques that also make use of unlabeled data for training, typically a small amount of labeled data with a large amount of unlabeled data. Semi-supervised learning falls between unsupervised learning and supervised learning. Semi-supervised learning is one of four basic machine learning paradigms. Machine learning, also referred to as ML, includes these four different types of learning paradigms. Supervised learning, unsupervised learning, semi-supervised learning, reinforcement learning. As a reminder, in supervised learning the training data have a label/class assigned to each input instance. The input data contain a collection of features as well as labels. The mapping of features to labels is where the knowledge is encoded. Then the model will map new samples into their correct labels. For example, if the task was to determine whether an image contained a certain object, the data for a supervised learning algorithm would include images with and without that object, and each image would have a label designating whether it contained the object. Data, labeled. In unsupervised learning the training data does not have a label/class assigned to each input instance. The input data do not necessarily contain labels or target values. The models extract meaningful representations from the data itself. An unsupervised learning algorithm builds a mathematical model of a set of data which contains only inputs and no desired outputs. The goal is to find structure in the data by, for example, grouping them. Data, unlabeled. Now, semi-supervised learning is a combination of the two previous approaches, with a portion of the training data missing the label/class. Data, both labeled and unlabeled. This is useful for a few reasons. The process of labeling massive amounts of data for supervised learning is often prohibitively time-consuming and expensive. What's more, too much labeling can impose human biases on the model. That means including lots of unlabeled data during the training process actually tends to improve the accuracy of the final model while reducing the time and cost spent building it. Many machine learning researchers have found that unlabeled data, when used in conjunction with a small amount of labeled data, can produce considerable improvement in learning accuracy. The acquisition of labeled data for a learning problem often requires a skilled human agent, e.g. to transcribe an audio segment, or a physical experiment, e.g. determining the 3D structure of a protein or determining whether there is oil at a particular location. The cost associated with the labeling process thus may render a fully labeled training set infeasible, whereas acquisition of unlabeled data is relatively inexpensive. In such situations, semi-supervised learning can be of great practical value. As a result, semi-supervised learning attempts to make use of this combined information to surpass the classification performance that could be obtained either by discarding the unlabeled data and doing supervised learning or by discarding the labels and doing unsupervised learning. Semi-supervised learning is a potent approach for use cases and fields like web page classification, speech recognition, genetic sequencing. Data scientists can access large volumes of unlabeled data in these fields, but the process of actually assigning supervision information to all of it would be an insurmountable task. Semi-supervised learning can also be considered a deep learning paradigm, since we can simply use deep learning algorithms in the same way we use machine learning algorithms on both labeled and unlabeled data. Let's say we have a web page classification task. The supervised model would learn to assign labels to types of web pages based on the labels that were inputted by a human during the training process. The unsupervised model would look at inherent similarities between web pages to place them into groups. The semi-supervised model would use labeled data to help identify that there are specific groups of web page types present in the data and what they might be. The model is then trained on unlabeled data to define the boundaries of those web page types and may even identify new types of web pages that were unspecified in the existing human-inputted labels. Cluster assumptions: the data tend to form discrete clusters, and points in the same cluster are more likely to share a label. This is a special case of the smoothness assumption and gives rise to feature learning with clustering algorithms. Continuity assumption: points which are close to each other are more likely to share a label. This is also generally assumed in supervised learning and yields a preference for geometrically simple decision boundaries. In the case of semi-supervised learning, the smoothness assumption additionally yields a preference for decision boundaries in low-density regions, so that there are fewer points close to each other but in different classes. Manifold assumption: the data lie approximately on a manifold of much lower dimension than the input space. In this case we can attempt to learn the manifold using both the labeled and unlabeled data to avoid the curse of dimensionality. Then learning can proceed using distances and densities defined on the manifold. Self-training: an algorithm that trains using the additional data and can be very useful in tasks like natural language processing and many others. The algorithm is the following. Mixture models and generative models. Generative approaches to statistical learning first seek to estimate the distribution of data points belonging to each class. The probability that a given point has label is then proportional to Bayes' rule. However, there is a main assumption: the data actually comes from the mixture model where the number of components, prior P and conditional P, are all correct. If the assumptions are incorrect, the unlabeled data may actually decrease the accuracy of the solution relative to what would have been obtained from labeled data alone. However, if the assumptions are correct, then the unlabeled data necessarily improves performance. The unlabeled data are distributed according to a mixture of individual class distributions. In order to learn the mixture distribution from the unlabeled data, it must be identifiable, that is, different parameters must yield different sum distributions. Gaussian mixture distributions are identifiable and commonly used for generative models. Mixture models and generative models. Traditional machine learning techniques like hidden Markov models and by extension general mixture models can be trained in a semi-supervised manner. Training methods like maximum likelihood estimate, MLE, maximum a posteriori, MAP, and M can work on semi-supervised data. Graph-based methods. Graph-based methods for semi-supervised learning use a graph representation of the data, with a node for each labeled and unlabeled example. The graph may be constructed using domain knowledge or similarity of examples. Two common methods are to connect each data point to its k-nearest neighbors or to examples within some distance. If data points I and j are similar, i.e. weight W is large, then their labels are similar. Assumption. Similar unlabeled data have similar labels. Co-training algorithm. Co-training is an extension of self-training in which multiple classifiers are trained on different, ideally disjoint, sets of features and generate labeled examples for one another. Initially, two separate classifiers are trained with the labeled data, on the two sub-feature sets respectively. Each classifier then classifies the unlabeled data, and teaches the other classifier with the few unlabeled examples, and the predicted labels, they feel most confident. Each classifier is retrained with the additional training examples given by the other classifier, and the process repeats. Assumption: features can be split into two sets and each sub-feature set is sufficient to train a good classifier. Low-density separation. This class of methods attempts to place boundaries in regions where there are few data points, labeled or unlabeled. One of the most commonly used algorithms is the transductive support vector machine, or TSVM, which, despite its name, may be used for inductive learning as well. Whereas support vector machines for supervised learning seek a decision boundary with maximal margin over the labeled data, the goal of TSVM is a labeling of the unlabeled data such that the decision boundary has maximal margin over all of the data. Example of SVM and TSVM. Assumption: unlabeled data from different classes are separated with large margin.